Anyway, okay. So let's talk a little bit about chapter 14 in fluids. There's really four things that you need to know, or four equations, or four types of problems. And the first is like these two homework. Can everyone see, by the way, I only need one of you to respond, but you guys can see my screen, right? I didn't mess up, I hope. Okay, cool, thanks, man. Thanks, Anna. So these first two chapter 14 problems, one is the hydrostatic difference in blood pressure of a human body. The second one's this elephant. I don't know what the third is. The third is Pascal's. So in these problems, and really in the final exam with the volcano, the first part of that problem, you had to find a pressure difference. And when you're only dealing with height, some kind of y-axis difference, the equation is quite simple. It's P2 is equal to P1 minus rho g H2 minus H1. Another way to remember this is just like energy. Think of it like energy. The way we did all those energy equations was we wrote down terms, right? So if you write down the pressure and the gravitational pressure is the density of whatever the fluid is. In a lot of cases, it'll be air. In this column with the hydrostatic difference of blood, it's blood. So Anna, we're going to have some comprehensive stuff, but really it'll be something like an energy problem or a projectile motion problem. So it's just the cumulative stuff. If you study the practice finals and go back and look at the other exams, technically just like projectile motion, energy, it'll be something like that. It won't be super hard, but it'll be something like projectile motion energy. So it's really all the problems, but I promise that it'll be either like blocks on a pulley or blocks on an incline or projectile motion. It won't be something like equilibrium and torques and all that good stuff. Okay. So anyway, back to this. This rho is the density of the fluid. If you're in air, it's the density of air. If you're in water, it's the density of water, whatever you happen to be in. These pressures are the static pressure on you. And this is important. If you were to go to the bottom of the ocean, that big P, P1 and P2, are the pressure on your body at every point. So I talk about this in the video, but pressure is a vector, but it's not a vector. We kind of think of it as a vector, but it's really a scalar. If you multiply it by the volume, it's energy. What pressure does is it pushes on the object at every point. So if you had a ball in the air, at every point it would be pushing with this same static pressure, okay? So it's kind of a vector, but it's not a vector. It's a vector on the surface that points normal to the surface. Just bear that in mind. We kind of want pressure to feel like a force that's pushing in some direction, but really when we say P1, the pressure vector at P1 pushes on the object. So it's hard to say what direction it has. It's not really a vector. These are really kind of energy without volume. They're energy over volume. But from this, you can see that you get P2 is P1 minus this stuff. And for problem 14 and 16, the only thing you had to do was find the change of pressure, which is negative GH2 minus H1. And the reason why, or the one weird thing here is you have to define Y or H to be positive up if the center of the Earth is down. If gravity's down, you have to define your H opposite of gravity, because this is the gravitational energy. So in this problem, all you would do is you would find your height. H2 minus H1 would be H2, well, it depends on the, yeah, anyway. If we defined H2 in this one to be 1.97 and we defined H1 to be 0, you would get a negative hydrostatic difference. So what they really want is they want you to go the other way. They want to know from the ground up. So, sorry, I'm trying to figure out why this is, trying to figure out a way to give you the positive difference here. Oh, I know. What they're doing is H1 is 0 and H2 is negative 1.97. That way this term will become positive. It's weird, I know, but just keep that in mind that they really just want the magnitude of the change, and depending on which way you take the change. Same thing in the second problem. The second problem is an elephant, and really all you have to do is use the height change to be 20 centimeters or 2.9 meters or whatever it is. But the density will be water. And in the density in this problem, they gave you the density of the blood. So that's not too hard to understand. And that's basically the first couple sections of that chapter were just about that the change in pressure is equal to the change in the gravitational pressure, rho g H2 minus H1. Okay, those are pretty easy. The next ones that we have are Pascal. And Pascal's principle is that everywhere inside, the pressure is the same. If you have a small opening and a large opening, then the force on the small opening over the area of the small opening is equal to the force over the second over the area of the second. I'm not even going to talk too much about that. That's a straight up easy calculation, right? It's just something to know that you have if you need it. We'll talk about it when we talk about the volcano problem, how we use it, because I used it in that. But this is super easy, I think. The only weird thing could be that the area, if you had like a circular piston, remember that the area of a disk is pi r squared. And if we do that by diameter, that's pi d over 2 squared, which is pi d squared over 4. But otherwise, what ends up happening is you end up having either the radius squared or the diameter squared over each other. It's not a huge deal. And then the block of wood problems, like the one that we did on the quiz. Now this is buoyancy. And buoyancy, really the equation is ma is the force of buoyancy minus the weight mg. However, mg for an object is its density times its volume. The force of buoyancy is the density of the liquid times the volume of the water displaced, or the volume inside that liquid, times g, okay? So what we end up with, if the object is floating, it has no acceleration, and therefore a is 0. And you end up with the liquid times the volume of the water in the liquid minus the object times the volume of the object times g. And when we did like the iceberg problem or the block floating, you can see that the g's cancel, and what you get is the density of the liquid times the volume of the water displaced, the amount of the volume of the object in the water, times the density of the object times the volume of the whole object. And when you do these problems, it's really simple. This problem's kind of nice because then you have to go back and you do it twice. But this isn't too hard to understand. We have a lab on buoyancy. I don't think this part's too bad. And I don't really want to spend too much time on that one either. So iceberg and oil. Basically, I gave you both of those types of problems. However, these last 3 problems are where things get hard and fluid. You have to know Bernoulli's equation, which mimics energy. And that says that P1 plus rho g H1 plus rho V1 squared over 2 is equal to P2 plus rho g h2 plus rho v2 squared over 2. And note, these are not volumes, these are velocities. The only other equation you have is that the area 1 times the velocity at 1 times the area 2, velocity at 2. This is a continuity equation. So let's talk about each of these things really fast. This is the static pressure. This pressure, don't let your intuition fool you. Your intuition actually says, like, if you put your thumb over part of a hose nozzle and it sprays, the reason why it's spraying is because the velocity changes, the kinetic pressure changes. The static pressure can end up being very different than what your intuition says. And then this is just the gravity. So really your job is to write down P1, H1, and V1, and P2, H2, and V2. But how you find these things depends on a lot of different things. And I gave you these 3 problems and a few problems in the test about this. But we'll go through each one of these and talk about each of these things. So let's talk about this garden hose first. This garden hose is flat. We assume that it's flat and that there's a sprinkler at this end. So the pressure coming in is P1, and it comes in with a velocity 1. And height 1, I'm going to say is 0. And then it leaves with P2 and V2 and H2. And H2, I'm going to say is 0. So we can get rid of these G terms. These terms go away for us. And so really what we have here is we have that P1, sorry, I want to look at what this problem actually says. The hose has a speed. Oh, this problem we don't even have to worry about. So the only thing they want to know in this problem is what is the velocity to? And so this is really a problem about the continuity equation that says that V1 A1 is equal to V2 A2. That has to be true. Why? It has to be true because water is considered incompressible for us. It's an ideal fluid, so the amount of water that passes any point has to always be the same. The same amount of water has to pass any point because it's incompressible. Think of a swimming pool that's all the way at the top so that any water you add will overflow. If I plug a hose in, any water I put in, water has to come out, right? Same amount has to come out. It's incompressible. So all we have to do is use this. They gave us the area of the hose internally, but they gave it as a diameter. So this is pi d squared over 4. That's the area here at 1. And then they said that there were 29 little holes, each with a diameter of whatever. So the area 2 has to be 29 times each of those little holes. That gives you the full area 2. They gave us V1. So we see that V2 is V1 A1 over A2. And if you do this, you get pi D1 squared over 4 over 29 times pi D2 squared over 4. Pi, force, cancel, plug in your numbers, and you're all good. This is a direct result, though, of the incompressible nature of water. What goes in comes out, okay? And that's it. The whole point of this problem was make sure that you understand how to find V1 and V2. And areas a little bit, but I'm sure that's not super hard. These last two, though, show a little bit about using Bernoulli's equation completely. So P1 plus rho G H1 plus rho V1 over 2 squared is equal to P2 plus rho G H2 plus rho V2 over 2 squared. Okay, and so B here we'll talk about. So we're given, again, we want P1, H1, V1, and we really should probably write down rho, P2, H2, and V2. And then remember that we have V1, A1 is equal to V2, A2. Okay, so this is our job here, is to find these things. They're asking us, what is the speed at the lower level? So they're really just asking us to find, I'm going to assume that this thing goes down, right? It just drops. And so I have H1 is higher than H2. Remember that they have to be positive up. They told me that it has a speed V1 of 4.8 meters per second, and that the cross-sectional area, I'm sorry, I really should write A1 and A2 here too, was 4.2 centimeters squared. You don't have to change them, and you'll see why in a second. And then it drops 10 meters. So if I assume this is 0, I can assume this is negative 10. And then A2 is 8.4 centimeters squared. Now V2, which is the first thing that they want us to find, is A1 V1 over A2. And you can see that that's going to be 4.2 squared, sorry, not squared, over 8.4 times 4.8. So half of this. And so I know this is 2.4 meters per second. And then they say, oh, the pressure up here is 1.7 times 10 to the 5th pascals. What is it at the bottom? Okay, so we want P2. And P2 is going to be P1 plus rho G H1 minus H2 plus rho V1 squared over 2 minus rho V2 squared over 2. So let's look at each of these terms. This was 1.7 times 10 to the 5th pascals. This was, let's say, 1,000 for water times 9.8. H1 was 0, so this is minus 10 because it went down 10 meters. And then finally, 1,000 over 2. What was V1? 4.8. 4.8 squared minus 2.4 squared. So this is actually going to increase. This is going to be a negative. This is going to be a positive. And I get here, I get 1,700,000 minus 9,800, 98,000 plus 500 times 4.8 times 4.8 minus 2.4 times 2.4. And I get 80, wow, why am I so off? What did I do weird here? What the heck is going on there? Why is that H1 minus H? Oh, because I'm dumb. This is not a negative. This is actually a negative 10. So this is a 10. Yeah, I'm stupid. Sorry about that, you guys. H2 is negative 10, so it's 0 minus minus 10. So that's a plus, which I should have known. Times 98,000, or plus 98,000, plus 500 times 4.8 times 4.8 minus 2.4 times 2.4. And I get 276640, which is exactly what they got. Sorry about that. Mess up with the signs. But anyway, the point here is that really you're almost always given one of the B's and like both of the areas. So you can find the other velocity from the continuity equation here. And then it's just a matter of plugging in your variables that you know from the problem and finding whatever they ask you for. How this gets weird is, imagine that this pipe at the bottom was open to the air. So it was flowing out here. And if it's flowing out here, then P2 has to be 0, or atmosphere really. So P1 and P2, P1 would be 1.7, P2 would be 1.01 times 10 to the 5th. We'll talk about that in a little bit, but we'll talk about that when we do the exam problems. But that's really the only wrinkle, is if anything is open to the air, the pressure, the static pressure at that point is the pressure of the air at that point. We talked about that with the bullet going through the big water tank problem. It's a little weird. It's against your intuition, because you go, well, wait, the water's flowing out of that pipe. How can the pressure there be essentially 0, let's say? And it's because the static pressure on the water there, it's 0. The water still has kinetic pressure due to its velocity, and it still has gravitational pressure, but the static pressure goes to 0. It's weird, I know. We'll talk about it more in a second. This problem is exactly the opposite of the problem I just did. This one is going up. Okay, so it goes up, and we'll just write H1, A1, B1, P1, and P2, H2, A2, and B2. You're given the diameter. So again, this is pi d squared over 4. You're given the diameter here. You're given the diameter here. The first diameter was 2.95. The second was 1.12. You don't have to change those areas as long as they're in the same units, because you're going to use V1, A1 is equal to V2, A2 to find it. You're told that the speed of V1 is 0.859, so 0.859 meters per second, and therefore V2 is V1, A1 over A2. But note that you're given the diameters here. So this is d squared over d squared. It would be 2.95 squared over 1.12 squared. I'm not going to do that, but. And then there's a change of height. So height 1 is 0, height 2 is 7.81 in this particular problem, positive. And then the final thing that we're told is, so we're told that the pressure is 150 kilopascals, which is 150 times 10 to the 3rd pascals, or 1.5 times 10 to the 5th pascals, okay? And we want to know what P2 is, and we want to know what V2 is. As I said, this is just V1 times D1 squared over D2 squared. P2 is P1 plus rho G H1 minus H2 plus rho over 2 V1 squared minus V2 squared. And you can plug in the numbers once you have it, and you got it, right? So again, nothing in this problem is super hard. What's hard is just knowing that you have the continuity equation to find the other velocity if you're given one and you're given the areas. You need to know the change of heights, and you need to know one of the pressures. What gets weird about this is, once again, if one of these sides is open to the air, and let's say your air has a pressure of 200,000 pascals for whatever reason, then that's the static pressure P1 or P2 at that point. We'll see that right now when I go into the exam. I'm going to talk about the volcano problem, and I don't remember what the other problem was. Where are the practice exams? Link PowerPoints, practice exams. So, final exam. Let's do this one first. So on this final exam, this is just an energy problem. A Newton's equation problem. This is an energy problem of the same problem as before, part 1 and 2 are doing it with forces and the energy, gravity. Okay, so we'll talk about this one first. So here, what I want to know is I have a bubble, and that bubble is in water. And that bubble is made of hydrogen, and it floats upward. And I want to know how fast it goes upward. And then when it gets into the air, I want to know how fast it goes upward. So basically what you have to know here is you have to use the buoyant force equation to find the acceleration as it goes up. And then you have to find the buoyant force in air. So it's basically doing buoyancy twice and using that acceleration to get the velocity. So we'll see that. Remember that your buoyancy equation is that ma is equal to the buoyant force minus the weight. And the buoyant force is the density of the liquid times the volume of water displaced times g minus the density of the object times the volume of the object times g. And that's equal to the density of the object times the volume of the object times a. So really, we can divide through by this, and we get density of the object times the volume of the object. So A is equal to PL over P naught, V water displaced over V naught, G minus G. Or we could really write this as getting rid of this, minus 1 times G. Now, we have some things that we have to figure out what they are here in this particular problem. For hydrogen, I give you that hydrogen has a density of 0.09 kilograms per meter cubed. I tell you that the volume of the bubble of hydrogen is a perfect sphere with a radius of 0.002. So the volume of the object, in this case hydrogen, is 4/3 pi r cubed, where r is 0.002 meters. You can plug that in. But we don't need to worry about that at the moment. First thing I asked was for the mass. Remember that density is mass over volume, so mass is density times volume. Plug that number in, plug that in here, plug that in, and you get the mass. Second thing that I wanted was I wanted to know, sorry, my dogs are walking around. If it begins, draw a free body diagram. So the free body diagram would be the buoyant force, weight, mg, and A, I'm guessing would be positive upward. You see bubbles rise in your soda, right? From that, I can get the acceleration using that equation. Note though, when it's in the water or even in the air, the volume of water displaced or fluid displaced and the volume of the object will be the same. So really, A is only the difference in density over the difference of the object minus 1 times g. And so my acceleration here for the liquid is water, that's 1,000. Hydrogen, I said, was 0.009 minus 1 times g. This is 1,000 divided by 0.09 is 11,000 times g, right? So this is 11, 11, 11, 11, 11, basically 11,000 times 9.8. That's pretty fast, right? And I don't know, I think I might have left off g on this solution. Yeah, sorry if I did. This is in the water, okay? I guess I should be a little bit more specific with what this is. If I multiply it by 9.8, I get 109, which actually sounds semi-right. 109 times 10 to the third meters per second squared. That's really fast, right? That's A in the water. A in the air is the density of the air. The density of the air is only 1.2. Okay, so this is 1.2 divided by 0.09 minus 1 is 12.3 meters per second squared. Once we have this, though, once we have this, how we find the velocities is this becomes a constant acceleration problem. If you go from h is equal to -2 to h is equal to 0 with an acceleration of 10 point or 109,000, right, meters per second squared, we know that if it starts at rest, v initial is 0, 2a times change of y, or h2 minus h1. So this changes 2, v initial is 0, v final would be 2a times 2, or 409, or 418,000 is 646. So v final is about 646 meters per second. Once it gets to the air. At the air interface, this was only 12.3 meters per second squared, and now our v initial is 646 meters per second. Plugging that stuff in, v final is square root of v initial squared plus 2a delta y, again 0 and then 2. So this is going to be again 2, which ends up being 646 squared plus 2 times 12.3 times 2. And you can see that this is barely going to change its velocity. Whatever velocity it gets to the air interface with, it's basically going to have like 646.3 or something, which is a little weird. You might think that it would keep accelerating and it would be going much faster after it traveled 2 meters up. It really isn't. It gains all of its speed under the water. I thought that was interesting. Okay. So this is really just a problem about buoyancy, and there's a little bit about constant acceleration in here, which is where the cumulative part of this test comes in. You have to know how to do this part. And then it says, oh, if it's an argon bubble instead of hydrogen, and really the only thing that changes is instead of 0.09, we now have a density of 1.78. What happens though is that is heavier than air. So 1.2 over 1.78 is less than 1. You're going to get a negative acceleration in the air. And so what I'm saying is, well, where does it end up? If you look at this, if it was positive acceleration going up to the interface between the water and the air, and then it was negative in the air, this thing's going to sit on the surface, right? That's a little weird. That's a little tricky. But it's like really the only interesting thing I could think of to deal with this problem. The last question here that I want to talk about is I asked, well, if your friend claims a balloon is an anti-gravity device, is it? Whenever I ask questions like that, I just want to know, I want to see your thoughts on things. I want you to think about density. I want you to think about how gravity works, why things rise. I think it's really weird that if everything's being pulled down the same, why does the air push something lighter or less dense than it up? That's kind of a weird physical process to think about, that in the presence of gravity, things settle to their densities, as long as they're liquids or gases. I shouldn't say things. Liquids and gases, any type of fluid, actually settles in layers of density. And that's because it can freely move, which is really odd. Or maybe it's not odd to you, but I find density of fluids really odd when gravity comes in. And really, there's no wrong answer there as long as you write something semi-thoughtful. But I want you to try to explain to me why a balloon isn't really an anti-gravity device. And the answer is, it's still subject to gravity. It's just that the buoyant force is overcoming gravity. So I guess in that sense, it's anti-gravity. Or in that sense, it's not anti-gravity. Gravity still affects it. I don't really know. It's your opportunity to tell me something that you've thought about or learned or think about density. Okay, so on to the other fluid problem. And the other fluid problem is the volcano. That last problem was pretty easy. I think this volcano problem is a little bit harder. So again, you'll notice that this exam starts off with a force problem with blocks and pulleys, and then it has a yo-yo problem, which is still kind of blocks and pulleys and torque. You won't have a torque problem like that though. Well, I guess you could, because these really use torque as well. So just make sure you understand those two. But let's go to the volcano. And this is actually real data that I used on some volcano. I don't remember where, but we're told that the volcano is a cone. So think of it like a nozzle of a hose, right? And as always, as I was saying before, what we want is at the bottom, we want P1, H1, B1, and A1. And at the top, we want P2, H2, B2, and A2. Okay. So what are we given here? We're given that, oh, and maybe density. We're given that this thing is 850 meters tall. So if we assume at the bottom it's 0, this is 850 meters. Hello? Oh, that was just someone's phone. And then we're told that the area at the top is 2 times 10 to the second, which is 200 meters squared. At the bottom, we're told that this is 4 times 10 to the 8th meters squared. So it has a base. And yeah, I know volcanoes aren't exactly cones, but they're pretty close sometimes. So we're going to assume this one is. Now, we don't know the pressure at the top yet, and we don't know the velocity at the top yet. I don't think. Oh yeah, we do, sorry. The magma leaves with a velocity of 63 meters per second. And you're told that the pressure inside the volcano at the base is 240 atmospheres. So remember that we always have to be in pascals, because pascals are Newton per meter second, force over area, or Newtons per meter squared, force over area. So the conversion rate here is, I really shouldn't have put that, is 1.01 times 10 to the 5th pascals in 1 atmosphere. So you need to multiply that to get the pressure. I'm not going to do that right now. It's not super important. But our overall job is going to be to find V1 and to find pressure 2, the pressure at the top of the volcano, the static pressure. Now, what is the air pressure up there? You know, at the surface of the Earth, that at the surface of the Earth, the air pressure is 1 atmosphere, or 1.01 times 10 to the 5th pascals. But we're not at the surface of the Earth. We're 850 meters up, which is significant. So again, P2 is P1 minus rho G H2 minus H1. Okay. Now H2 is 850 meters, and P1 we said was the surface of the Earth. We want, make sure you're clear on this, we want the pressure at the top of the volcano due to the air, not due to the inside. They will be the same, they have to be the same, but we're going to find the pressure due to the air at the top, because we know the pressure on the top of this thing, if it's open to the air, has to be the same as the air. That's the static pressure acting at the top of the volcano. It has to be continuous, which means the pressure on the inside the volcano at that point also has to be the same as the pressure on the air. That's a little weird. It's stuff you'll get into later on in higher physics, but trust me that at this interface, the pressure has to be the same. Hang on a second. Now, at that interface, the pressure is 1 atmosphere, so 1.01 times 10 to the 5th pascals, minus the density of the air, times G, times H2 minus H1, which is 850 meters. Just doing some real fast math here, this is 12 times 850, basically. 12 times 850 is only 10,000, so this is going to be essentially 101,000 minus this answer. It's going to be about 9,800 pascals, something around there. That is the pressure at the top of the volcano. That is P2 back here. So if this is 9,800 pascals, okay, we have everything we need to solve for V1 or V2 or whatever we want. What we're actually going to solve for here is the density, which is a little weird. But before we do that, let's talk about V2 and V1. We have V1A1 is equal to V2A2. Now, I want you to prove that V2 or V1 is essentially 0. So let's look at V2 times A2 over A1 is V1. So it's opposite of what we normally do, right? But this stuff here, V2 is 63. A2, we said was 2 times 10 to the 2nd, so 200, over 4 times 10 to the 8th. Just looking at this, I can see that that's 63 divided by 4 times 200 is 3,153 times 10 to the 3rd over 10 to the 8th. This is going to be like 3.18 times 10 to the minus 5th meters per second. That is so tiny, because if we go back and look at the equation, well, I guess I haven't written it yet. We know that this equation is P1 plus rho G H1 plus rho V1 squared over 2 plus, nope, not plus, equals P2 plus rho G H2 plus rho V2 squared over 2. Okay. If V2, or I'm sorry, if V1 is this small and you're squaring it, this term is essentially 0, right? It's 10 to the minus 10. So we can neglect this term. And that's what I'm getting at. I think it's question 3. Is the velocity of the magma at the base sufficiently close to 0 to ignore? Yes. If you go back to the problem where the guy shot the water barrel, and it talked about how the water level drops so slowly in the water barrel as the water flows out of the bullet hole that it's essentially 0. That's what we're saying. So we can ignore the V1 term. We also know that H1 is 0, so we'll ignore that term. And what we get is we get that P1 minus P2 is equal to P or rho GH2 plus rho V2 squared over 2. And I want the density rho. So density is P1 minus P2 over GH2 plus V2 squared over 2. And plugging these numbers in, P1 was 240 atmospheres, so 240 times 1.01 times 10 to the 5th pascals per atmosphere, minus 90,800 pascals over 9.8 times 850 plus 63 squared over 2. And this is going to give you something like 2,400 kilograms per meter cubed. Okay. So all we did, though, algorithm-wise, is we first found our variables. And then in order to find B1, we use the continuity equation that B1A1 is equal to B2A2. And then we got H1 and H2 from the picture. We were told what P1 was. We had to find P2 using that pressure equation, that really simple pressure equation. P2 is equal to P1 minus rho G H2 minus H1. What you had to know, though, was that this was the pressure of the air here, right? So once you have that, you have P1 and P2, you have B2 and B1, you have A1, A2, H2, H1. The only thing left to find in this problem is the density. And the density of lava, it turns out, is around 2,400 kilograms per meter cubed. Okay. This asks you to do this symbolically. So what I'm asking you for is this equation here. And then I'm asking you to solve it for rho. Now, if these last two problems, if the volcano is capped so that pressure can flow in but nothing can flow out, Pascal, his principle, says that F1 over A1 is equal to F2 over A2 everywhere if it's incompressible, okay? So we know that the force, okay, is equal to F over A. So P1 is 240 atmospheres, and that's equal to F2 over A2. If I multiply this 240 atmospheres in terms of pascals, 1.01 times 10 to the 5th pascals, and then I multiply it by the area 2 that's given here, 200 meters squared. This is force over meter squared, so this is force. I get the force. And that force is going to be pretty huge, right? It's going to be 48 times 10 to the 3rd times 10 to the 5th. It's going to be 48 times 10 to the 8th newtons. That is the force on the inside cap of the volcano, which is pretty easy to figure out. Girls, come here, come here. Maddie, 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 Maddie. Sorry about that, my dogs are being annoying. Okay, so we have Pascal's equation that tells us force over area 1 is equal to force over area 2, but I gave you force over area as a pressure, okay, that you had to change to pascals. And the final thing is just knowing that P times V is energy, and I gave you the volume of the cone. I could have made you guys integrate it. I'm not going to make you integrate a cone to get this result. So I gave the volume, and you just have to know that 240 atmospheres times 1.01 times 10 to the 5th pascals per atmosphere times this volume gives you the energy stored inside that volcano. And it's a huge number. It's a really, really big number. Something like 10 to the 15th or 10 to the 16th joules. Really, the only reason why I wanted you to see that is I wanted you to know how much energy is stored in the volcano and why, when they erupt, really bad things happen. So anyway, I thought it was a fun problem, better than doing a hose or a shower head or something weird. Hopefully, as a wrap up, hopefully this has all made sense. For fluids, you need to know P2 is equal to P1 minus rho G H2 minus H1. You need to know Bernoulli's equation that says F1 over A1 is equal to F2 over A2. I'm sorry, pascals. I think I just said Bernoulli. you need to know, and this only gets weird because H has to be positive opposite the direction of G. You need to know MA is the buoyant force minus mg, which is equal to the density of the liquid times the volume of the water that's placed in the liquid, how much volume is in the liquid, times g minus the density of the object times the volume of the object times g. And then finally, Bernoulli's equation. I guess I don't need that one there. And the last thing that you need to remember is the continuity equation gives you V1 A1 is equal to V2 A2. Those are the equations for any fluid problem. The only weird thing is sometimes you have to find the pressure at one point or another, and you usually have to find it for air. Like in the volcano, the beginning of the volcano problem, you had to find the air pressure at the top, and then remember that any pipe or thing that the liquid's flowing in, if it's open to air, the pressure of the fluid at that point, the static pressure P, is equal to the pressure of the air. Now, one thing I will say that kind of makes these things a little bit harder for me than for you is it's really easy to mess these up so that they don't make any sense. So I'll try to make sure that the final exam problem with this makes sense. If for some reason it doesn't, you'll all get credit for that part. But yeah, as you guys go forward with this, just know that if you're trying to set up random equations or random problems, you can get in a lot of issues because this stuff won't make sense if you do it wrong. But the algorithm for all of these is just finding H2 or H1, finding A1, A2, and F1 or F2, finding the volumes of the fluids or knowing that they're the same so that you can cancel them. Know that if an object is floating, A is 0. And then finally, these solve for V1 or V2 using the continuity equation, get H1 and H2 from the problem unless you have to solve for them, get P1 and P2 from the problem. So really, if you do a couple of them, you should have this down. There's really not a lot. Once you do 3 or 4 of these, you've got these problems. These aren't like a lot of physics problems where there's all these weird twists and turns. The only real twist here is you might have to figure out what P1 or P2 is by knowing that it's open to the air. So any questions on fluids? I know we just covered a whole bunch of fluid problems, but I think they're pretty easy to understand. I think I gave you every weird wrinkle that there can be with the hydrogen argon problem, this problem, the elephant, the pipes, all those things, okay? So if you're gonna study, just make sure that you understand the mechanical solution to each of these, like what equation you use and how you do it, and where you got your variables from. These you can memorize, which is really nice that you can actually memorize things here. A lot of times we can't memorize equations. They don't help us. We have to understand the physics, right? When we do torque with Newton's laws, you have to know all the different forces and you have to know how the torques work and blah, blah, blah. These you can almost get away with writing down equations and plugging in variables, to be honest. Okay, if there's no questions on fluids, I want to go to gravity. Gravity is chapter 13, and it breaks down into 3 different things. Your book actually doesn't put a lot of emphasis on Kepler's laws. I do. So we have 3 things. The force of gravity is G m, little m over r squared, which means that this is ma, little m cancels, and you get that A is G times whatever's causing the gravity times the distance. Now, for you, standing on the surface of the Earth, big M is the Earth. It's causing the gravity that's accelerating you down towards the core. For the Earth, the sun is big M. right? Whatever is causing the gravity is the big M, and the little m is the object that you care about being accelerated or in motion. Now, remember that it's a third law pair, which means that while the Earth pulls down on you with an acceleration of 9.81, you pull up on the Earth with a different acceleration. The acceleration that you would pull on the Earth would be g times your mass times r squared, which would be insignificant. It's like 10 to the minus whatever. And remember that g is 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. The units aren't that important, but this number is, okay? R is the distance between the two objects. Second thing is Kepler's laws. And we'll go through these again, but from a ellipse, RP plus RA is 2A, RP plus EA is A, and RA is A plus EA. All right, sorry about that. My wife just came home. My dogs go crazy whenever my wife gets home. So we have these from the ellipse. And then we also have this period equation. And this period equation is a little weird because, actually, I'm going to talk about it on the next page. The period equation is for anywhere in the entire universe. This is true for an object rotating. If t is in seconds and a is in meters, what you do is if you were around some weird planet, g is 6.67 times 10 to the minus 11, m is the weird planet's mass, t would be your period in seconds, a would be your semi-major axis. However, if we are in our solar system and this is the mass of the sun, so anything going around the mass of the sun, it turns out if t is in Earth years, a is in something called AU, then all you have to do is t squared a cubed. That works for Earth. Earth has a period of 1 Earth year. It goes around the sun 1 year. And it has a radius, a semi-major axis radius of 1 AU. That's obvious, right? The conversion rates are pi times 10 to the 7 seconds per Earth year. So you can put that back in seconds if you need it. And 1.5 times 10 to the, I keep forgetting this, I want to say it's 10 to the 11. And I know I got it wrong the other day. I realized I was doing it wrong, so thanks. I don't want miles, I want meters. Yeah, it's 1.5 times 10 to the 11. So 1.5 times 10 to the 11th meters per AU if you need to convert it for some reason. Usually though, you'll just plug it in. So I'm not going to do this quite yet. We'll come back to this. The other thing you need to know from gravity, and the final thing really, oh wait, there's one last thing here, and that's that the velocity at perihelion times the radius of perihelion is equal to the velocity at aphelion times the radius at aphelion. I gave you a problem where these were converted into omega. Remember that r omega is b, b is r omega. So this becomes omega p rp squared is equal to omega a squared ra squared, right? All right, the last thing you need to know for gravity is that the energy in gravity, you write for each position, this is mv squared over 2 plus the potential, so this is the kinetic. In gravity, we rewrite this as 2r minus gmm over r. Okay, so the potential energy, which used to be mgh, is now gmmr. And the kinetic energy can be written either way. It's really up to you. We'll go through a few problems and talk about that. Homework, I believe 7. Was it 7 or was it 9? Nope, 9 with fluids. It's homework 8. Homework 8 was all the gravity problems and a few of this angular momentum stuff, these 11, which was just I omega is equal to I omega. Well, let's look at a few of these. This problem is straight up F equals gmm over r squared. All you had to do was put the masses in and the distance between them and g in and find the force. This problem is if you have a black hole above your head, so if you're standing here, you have a force down, which is mg, and you have a force up due to some black hole, which is ma, and we want a to equal g, which means that if this is mg, then, or really, I should say, if this is ma, then a is gm over r squared, and it asks you at what distance, so r is equal to gm over a, where that's the mass of the black hole, that's 6.67 times 10 to the minus 11. A has to be equal to g. That's just a little bit of algebra manipulation to find r. I think you guys probably get those really, really easily. This problem, it starts off by giving you a period. So remember, this is about a comet going around the sun. And as I said, we have RP plus RA is equal to 2A. RP, remember that the sun is at one focus, so RP is when it's close, RA is when it's far. RP plus EA has to be A, RA has to be A minus or A plus EA. And it's in our solar system, so T squared is equal to A cubed if T is in Earth years and A is in AU. So the first thing they ask us is, what is the semi-major axis? That is A. We want A. A is the third root. If you hit the math button on your calculator, it will give you the third root of this. What is T? It's the difference in these years, 13, 16. So this would be third root of 13, 16 squared. Once you get that though, your answer will be in AU and you need to convert it by 1.5 or 1.49 times 10 to the 11th meters per AU to get this answer. Big old answer. Then what is its greatest distance from the sun? Well, that's RA. So once you have A and you have EA, or once you have A, you can multiply 1 plus E. They gave us E here of 0.985. So plug in A times 1 plus, so multiply whatever you find for A by 1.985. And you've got it, right? This question is just basically using Kepler's equations. Kepler's 3 laws really boil down to this. Kepler's first law is that they're ellipses. That tells you RP plus RA is 2A. RP is A minus EA. RA is A plus EA. T squared is, nope, I don't want to do that one yet. That's his first law, that they're ellipses. And that's the equations of ellipses, just geometry. His second law tells you that VA times RA is equal to VP times RP. Or, again, if these are in omega, omega A RA squared is equal to omega P RP squared. And then finally, his third law tells you that the period squared is equal to the semi-major axis cubed. Newton proved that this was true, though. Kepler just said T squared was A cubed. Newton gave it for everything, 4 pi squared over G. Okay, and we'll see that on the test. I gave you a problem on the test where you had, and I think I give you the next problem has this. So this is a satellite in elliptical orbit, and we're not told that it's in our solar system. So in this problem, we're given the period, and we're told the mass of this guy. And we're told that at aphelion, it has R. So let's look at what we're given. We're given T squared, or no, we're not given T squared. We're given T. We're given M of the thing that it's rotating around, big M. We're given RA, and we're given omega A. And we're asked to find what is the angular speed. So let's reverse engineer this. We know omega A is RA squared is equal to omega P is RP squared. And we're asked to find omega P. So this is omega A, RA squared over RP squared. We know RA, we were given RA, we need to find RP. We have that RP plus RA is equal to 2A. So if we knew A, we could get RP, right? In order to get A, we can use T squared is, I keep wanting to do that, 4 pi squared over GM, A cubed, or A is cube root of GM T squared over 4 pi squared. T has to be in seconds here. A will be in meters. G is 6.67 times 10 to the minus 11. M is given. We do this, we find A. We plug in 2A minus RA, we get RP. We plug that in here, we get omega P. And that's how you solve this problem. I hope you see that for Kepler's laws, it really just comes down to plugging numbers into equations. You're usually given 3 pieces of information, and from that, you'll find all the other information, right? This stuff, I'm going to talk, well, I'll talk about it right now. We're assuming here, well, the point of this problem was to make sure that tomorrow's lab, honestly, Anna, it's not going to take that long, and I need to finish writing it, but it'll probably take all of an hour, if even that. It might not even take that long. I'm designing it so that you can do it tomorrow during the hour that we're talking, and we'll all be together online if you want. But I probably won't post it today. Maybe I will, but I'm not going to guarantee. It's not meant to be hard, though. Trust me. It shouldn't take up a bunch of time tomorrow. No more time than what we normally do with these meetings anyway. Okay, so this problem was meant to help you understand concepts like total energy, potential energy, kinetic energy, and orbital speed. Now, the potential energy is GMM over 2R. With a over R with a minus sign. The kinetic energy is GMM over 2R, and the total energy is PE plus KE, which is GMM over 2R minus GMM over R. If I subtract these, multiply this by 2 over 2, I see that the total energy is negative 2 GMM over, negative GMM over 2R. Okay, so it's the negative of the potential. Oh, my brain. This is kinetic energy plus potential energy. It's the negative of the kinetic energy is the total energy. If you want to know what the total variation in energy between aphelion and perihelion is, well, it's 0. Energy is conserved, right? This weirdly, you have to be careful because this isn't necessarily true. GMM over 2RA cannot be equal to GMM over 2RP, right? Because that would say that RA and RP are equal, and that would only be true for a circular orbit. But you can say that the energy here has to be equal, which means that they should cancel each other out. Whatever it loses in potential, it gains in kinetic. Whatever it loses. So really what's true is GMM over, this is like really weird, right? The change in kinetic energy. So let me write, the change in kinetic energy should be equal to the change in potential energy, which gives us times 1 over 2 RA minus 1 over 2 RP should be equal to negative GMM 1 over RP minus, RA minus 1 over RP. But what I'm going to tell you is this is messy. Really, the change in energy is 0. You know that from conservation of energy. It gets messy because these RAs and RPs don't cancel right when you're in this. It actually works better when you do mv squared over 2 minus GMM over RP is equal to, and I know that seems weird, but it's really easy to get things that don't actually make any sense when you're doing these RAs and RPs. Anyway, regardless, the change in energy is 0, energy is conserved. The potential energy change and the gravitational energy change, you can find those right here. This is the potential energy change. This is the gravitational energy change. They tell you RA and RP. RP is the close one. RA is the furthest away one. So you can find this is the change in kinetic. This is the change in potential. They are equal, right? Which is odd, but they are equal. And then finally, the change in orbital speed is hard to do. I do it in the solution. I'm not going to do it now. It takes a little bit of time to figure out. But you can just actually solve this for V and solve this for V. So the shorthand notation of it is solve mv squared is GMM over RA squared. Solve this for VA, do another equation for VP, take the change of them, and you'll see that it ends up being 0.99. I won't ask that on a test. In fact, I probably won't ask about gravitational energy on a test. Why do we need it? We need it because we can't define the gravitational potential energy as mgh anymore when using universal gravity. Final two problems are, this is just to remember that for circular orbits, anything going around in a circle, there is an ARAD if it's going around with some velocity. ARAD is v squared over 2. And ARAD is also equal to the force, the acceleration due to the force of gravity. Okay. So if this is equal to v squared over 2, you can see that v is equal to 2gm over, I'm so sorry, I'm being dumb. It's not 2, it's r. So this is square root of gm over r, yeah, no, that's fine. So yeah, v is equal to gm over r, and what they're really asking you though is to find the acceleration in terms of g. So if I take this acceleration as gm over r squared, divide by g, I get it in units of g, because that technically means I'm multiplying by g over g. When you do that, all you're doing is plugging in the different r's. And what is it saying here? Oh, I'm sorry. There is one weird thing here. One really, really, really weird thing here. So t squared is equal to 4 pi squared over gm times a cubed, okay? But we're going to consider this to be a circle. If a is equal to gm over r squared, then a times r, right, is equal to gm r over r squared, which is gm over r. Now, looking back at this, v squared is equal to gm over r, and mv squared over 2 is equal to gm m over 2r, which is the potential energy, or the kinetic energy. And it wants us to calculate the accelerations. So it's giving us the period. It's giving us t squared, and we know that t squared is equal to, well, actually I take that back. We know that t is 2 pi over omega, or it's t is b over r, so 2 pi r over v, right? So we can get v is 2 pi r over t, and then mv squared over 2, sorry, take that back again, and then v squared over r is our a. So a is equal to 4 pi squared r squared over t squared. It gives you the period in days and years, and it gives you the radiuses in meters. So turn these periods into days, I'm sorry, turn them into seconds, and get the acceleration. That's not too hard. I'm thinking of the second part of this, or the next problem when I'm talking about this a and g. This is all you needed to do. T is 2 pi r over b for circular orbits. Plugging in v squared over r is a, and you get that. This next problem was the one that I wanted to talk about. No, it's this one, 1339. The escape speed is 922 kilometers. Sorry, radius. R is 922 times 10 to the third meters. And we're told, I want you to go away. We're told that the acceleration, A, is 1.06 meters per second squared. So how far from the surface will the particle go if it leaves the asteroids with a radial speed of 10.9? Now here's the thing. This is what I was trying to talk to you guys about. Since ma is equal to gm m over r squared, a is equal to gm over r squared. Or if I multiply, and I can consider these big R's, AR is gm over r, okay? Why do I care? Because the potential energy and the kinetic energy, the potential energy is gm m over r, and the kinetic energy was gm m over 2r. And so what I can see here is that this is actually a times r times m, right? And this is actually a times r times m over 2, okay? Now, I don't need the little m, and I'll show you why in a second, or I'll show you why right now. But remember that you can write energy 1 and energy 2. And so as it leaves the surface and it goes out to here, it leaves with V is equal to 1.06, no, 1090. It leaves with 1090 meters per second, okay? And we want to know how far away it goes. Remember that this is R, the original R. So we have GM M over 2R minus GM M over R is equal to GM M over 2R plus H, and H will be however far away it gets, plus minus GM M over R plus H. Now, all the little m's cancel. And because this is A, right? So what I get here is I get A to the half minus A at the surface is equal to, if I multiply through by R over R, right? Do I want to do that? No, I want to leave that alone. I want to solve this for H. So let me do this. This is A times 1/2 minus 1, or minus 1/2 A, is equal to GM over 2R plus H minus GM over R plus H. So this whole thing is A times, this becomes, let me actually do something different here. This becomes minus GM over 2R plus H. If I multiply by that, I get that this is A to the half times 2 times R plus H is equal to negative GM. Dividing through, why am I getting a negative sign there? Oh, because they're both, this is negative half. So the negative sign can go away, and what I see is that I get 2 GM over A is equal to 2R plus H, or 2 GM over A plus minus 2R. Minus 2R is equal to H, and because A is GM over R, right, this becomes 0. I don't know what the heck I'm doing. I'm being stupid. Sorry, guys. My brain completely just checked out on that last problem, and it's still going. Oh, I'm so dumb. I'm beyond dumb. Forget everything I just did. We're going to start this problem over, and it'll go really quick. So GMM over 2R plus minus GMM over R, where R is the radius of our satellite. This is E at the radius of it. So when it's here. And then it shoots out to some distance H. And at that point, it stops moving. This is kinetic energy, this is potential energy, which means the energy here is all potential. So this is minus GMM over R plus H. Okay. Now, what that means is we get GMM over 2R minus GMM over R is equal to minus GMM over R plus H. Yeah. Okay. Now, we can get rid of all the GMMs, right? To be honest with you. And we would get 1 over 2r with a negative sign is equal to negative 1 over r plus h. And therefore, I can get rid of the negative signs. I can get r plus h is equal to 2r. And that means h is equal to r, right? Pretty simple. That means that it has to go out r. Is that what they got? Why didn't they get that? They got oh, I know why. I'm still being stupid, you guys. All right, I'm gonna stop messing with this in a minute and just go to the test. But I see what they did, which I'm being stupid about. mv squared minus gm m over r is equal to minus gm m over r plus h. Yeah, I'm so sorry, you guys. All these m's cancel. I get v squared over 2 is equal to gm over r is equal to minus gm over r plus h. This is a times r. This is minus gm over r plus h. And therefore, I get that r plus h is equal to gm. It's not a minus sign, it is a minus sign, over v squared over 2 plus a r, right? And h is equal to gm over v squared over 2 plus a r is equal to minus r. If I multiply by 1 over r, what I get here is I get r over r, I should say. I would get ar squared over v squared over 2 plus ar minus r. All I did was I multiplied through by r over r, r over r. And that becomes gm over r becomes ar times another r is r squared. Doing that, you get, plugging in these numbers, you could actually even further simplify that, but that's the answer. It's in the homework solution. I'm sorry, I completely messed that up this morning. I was trying to get to this whole fact that A is equal to gm over r squared, which means that ar is gm over r, which sometimes helps, but I was being dumb. Now, let's go back to this problem. And this problem says, we want to lift a satellite to a height equal to the kinetic energy of that orbit. Now, they're not telling you this, but assume that you want to get it up to energy 2 from energy 1, right? They're not telling you that you're to assume that it starts at 0 velocity and it starts at r. The energy here is gm m over 2r minus gm m over r, or mv squared over 2 initial minus gm m over r initial. If we take this to be 0, this is mv final squared over 2 minus gm m r final. Now, this is really, let's say, r plus h, and this is r. So what you get is that the change in kinetic energy has to be mv final squared over 2 minus mv initial squared over 2, which is 0. Another way to write that is it's gm m over 2 times 1 over r final minus 1 over r initial. And the potential energy is gm m, change in potential energy, R final with a minus sign minus a minus GMM over R initial, okay? And that is GMM 1 over R initial minus 1 over R final. Let's compare these two. I got GMM over 2 times 1 over R final minus 1 over R initial. We're assuming that R final is bigger than R initial, right? Which one requires less energy? Well, this is only half. This is going to essentially all be GMM over R initial. Take R final to be infinity and look at the difference between these two energies, right? When you do that, you can see that the energy for lifting against its potential is always going to be greater. The bigger this R final gets, the smaller the potential energy needed, or the energy needed for kinetic energy. So the lifting energy is always going to take more energy. That's because the change in potential energy is always going to be GMM R initial minus GMM R final. And however far away you go, it's always going to be this term, right? Because R final will always be bigger. However, this, right, is always going to be half of whatever, even at its biggest. If R final was infinity, this term is always going to be half of that term. And so you can see that the energy required to overcome the change in potential energy, the energy you have to put into it due to the potential energy that's being stored by gravity is always greater than the kinetic energy that you need to get it up to speed in orbit. I know that's weird. It's a weird idea. I honestly confuse myself, obviously. I think a lot of students confuse themselves with this whole energy thing because of the negative signs and things canceling weird. So I'm not going to even ask about this stuff. I am going to ask about Kepler's laws and the universal law of gravity, but this stuff is always a pain and it's always a mess. So let's go to the gravity problems really fast on the two exams. So this 61755, the gravity problem is the third problem. What you can see here is that you have an asteroid that is, you're told, and shown in the picture, that you see there's an asteroid that is at aphelion while the Earth is at aphelion. And that asteroid is 3.066 AU from the Earth, not the Sun. That's RA from the Earth. So its RA from the Sun will be both. RA of the asteroid will be the distance to Earth plus the distance from the Earth to the Sun. I hope that makes sense to you. Now, you're given the Earth's eccentricity, and you're told that the asteroid is a perfect sphere. So the asteroid has a period of 7.912 Earth years. What is its major axis in AU? Again, T squared is A to the third if we're in our solar system, right? So A is third root of 7.912 squared. Easy enough. Once you find A, right, what is the aphelion distance of the Earth? Well, you know the Earth. So RA is RA plus EA. Hang on. I always forget this. What am I doing? It's A plus EA. For Earth, RA or A is 1 AU. So this is 1 AU times 1 plus E of the Earth. You're given that E is 0.167, right? Plug that in. What is the aphelion distance for the asteroid? Well, that would be RA for Earth plus 3.067, the distance from the asteroid to the Earth, wherever I wrote that, 3.066, plus RA of Earth. So you just add those. And now you have RA for the asteroid. What is the eccentricity of the asteroid? Well, RA is equal to A plus EA. So E is equal to RA minus A over A. That's pretty easy. The average angular acceleration of the Earth is 2 times 10 to the minus 7. Give the ratio of the average angular velocity of Earth to the average angular velocity in terms of their periods. What is the average angular velocity of the asteroid? Now, T for Earth is 2 pi over omega. And T for the asteroid is 2 pi over omega for the asteroid. Therefore, T of the Earth over TA is equal to omega A over omega Earth. And we can find omega A from that equation. We know there are 2 periods. We're told that, oh no, we're told somewhere that the period, oh, the asteroid is 7.92. So omega A is the period of Earth, period of the asteroid times omega of the Earth, which is 2 times 10 to the 5th, 10 to the minus 7. So this would be 1 over 7.912. I don't know why it keeps doing that. 7.912 times 2 times 10 to the minus 7 rad per second. And you can see that this is going to be very small, smaller than the Earth, right? It's traveling slower than the Earth at aphelion. That should make sense. Once you do that, I want to know how far in radians does this thing travel before the Earth catches it again. This is a little bit of a weird problem. So the Earth will go all the way around and come back to wherever the asteroid is, right? The distance the Earth has to go is 2 pi plus delta theta. The distance the asteroid has to go is only delta theta, but they're the same, right? So for Earth, 2 pi plus delta theta is the distance it travels. If it does that in, if it has an average angular speed, that over time has to be equal to, sorry, I'm being weird again. So this would give you the time is 2 pi plus delta theta over omega of the Earth is the period of the Earth, or the time of the Earth. The time for the Earth is 2 pi plus delta theta over omega of the Earth. That's equal to the time for the asteroid to go delta theta of the asteroid times omega of the asteroid. And if we want to know what delta theta is, or if we want to know what time is, let's solve this for delta theta. We get delta theta is WA over WE times 2 pi plus delta theta. So moving that over, we get 1 minus delta theta is 2 pi times omega A over omega Earth. Or I guess we could actually do that. Do I want to do it the other way? Yeah, I want to do it the other way. I think it's actually easier to see the other way. Let's do this. Multiply through by that, omega E over omega A times delta theta is 2 pi plus delta theta. If I move that over, I get the delta theta is omega E over omega A minus 1 is equal to 2 pi. And finally, going up here, we get that delta theta is 2 pi divided by omega of Earth over omega of A minus 1. This is actually some semi-big number. You can find it. When you find it, you're going to find out that this is something like 2 months. It's like 59 days or something. Because when you divide this through, you find that this is a sixth of 2 pi, whatever. So what is, this ends up being something like 6, right? Oh, yeah, it ends up being 7.92 minus, so divided by 7. 2 pi divided by 7 is about 0.897. That doesn't seem to make sense. It's 2 pi. Yeah, I know that that's 7.912 times minus 1. And 2 times pi divided by this answer. It's 0.909. Oh, right. This is 0.909 rad. And that is, if you divide that by 2 pi rad, what you'll get is you'll get the ratio, okay? Sounds weird, but what you want is you want the ratio of a circle. So we know that this thing goes around and it travels a distance of 0.909 rad. There are 2 pi rad, so there are 6 rad around. So 0.909 divided by 2 pi is basically 0.14 of a year times 365 is 53 days. This is about 53 days. That means for about 2 months, it's going to take about a year and 2 months for the Earth to catch up to the asteroid again, passing the asteroid again. That is about 14 months, which means if you were this astronaut, you would be trapped on the Earth or on the asteroid for 14 months before the Earth came back by again. That is a little weird and takes a little bit of thought about the geometry. But basically, in 1 year, the Earth goes around 2 pi. During that year, the asteroid travels some angle. Then it travels an additional angle and finally catches up. At that point, the Earth has gone around 2 pi plus delta theta. At that point, the asteroid has gone only delta theta. Those two things, if you divide by omega of the Earth and omega of the asteroid, those 2 times are equal, assuming circular orbits. Setting them equal, you can solve for delta theta if you know omega E and omega A, and we already do. And then finding that, you can find out how far it traveled in radians versus 2 pi, and use that to get the number of days or seconds or years that it took to travel that distance. And you can figure out for the Earth, I mean, you can figure out how long it takes until the Earth comes back. That's all well and good. That's just a weird problem to make it more interesting. The other problem that I think comes up in this exam is with pendulums. Pendulums, you need to know that pendulums often, this is a little bit for tomorrow, but T is 2 pi L over G for a simple pendulum, right? But on a, or anywhere, where G is not 9.81, G is actually Gm over R squared, because the force of gravity is mg, which is Gmm over R squared, right? Just don't forget that in the pendulum's equations, you sometimes need to use that. Last thing I want to do is look at the other test, because I don't remember what the, I do remember vaguely what this was. So for 3, in this one, all you have to do is we're trying to find the semi-major axis and a few other things for the Milky Way. You need to know that the Milky Way is actually traveling, or the sun is actually traveling around the center of the Milky Way. And we want to find the mass of the Milky Way, of our galaxy, from this. Now, we're told the orbital speed and the semi-major axis and the eccentricity. So if we're told A is 2.46 times 10 to the 20 meters, and we're told that V, we're going to assume that this is VA. We'll find that out in part 2. 2.4 times 10 to the 5th, meters per second, and we're told that E can be assumed to be 0.06 for the sun around the Milky Way. Now, the reason why we don't know the eccentricity is the sun actually changes velocity in weird ways due to all the other mass. We're going to assume that's not true. Now, the kinetic energy can be used to find the mass of the galactic center. We know that Ke is GMM over 2RA, and that's equal to MVA squared over 2, where these are the mass of the sun. So, since you have mass of the Milky Way is VA squared times RA. The 2's cancel and go away, and you divide that whole thing by G. Okay? Is that right? Have I forgotten something? Nope, that's right. So you can find the mass of the Milky Way. You're going to find it something huge. Okay? When you do find that, once you know that the period from Kepler's third law, T squared is 4 pi squared over G M of the Milky Way that you just found, A cubed. Taking the square root of this will give you the period. But remember that A has to be in meters, this has to be in kilograms, blah, blah, blah. Once you find this though, okay, you're going to find it's something, it ends up being like 20 times this number. If you take the period of, or the time since, the time since the Earth formed, and divide that by the period of the sun around the Milky Way, it'll give you, it's actually a 20th of this, it'll give you the number of orbits that the sun has made since the Earth was quote unquote formed. And when I say quote unquote, we don't know exactly when it came together as the Earth. The other thing that it asks you is for the force of gravity acting from the Milky Way onto the Earth, onto the sun. The force between any objects is Gm of the Milky Way, m of the sun, divided by the distance between them, okay? And if we assume that this is RA at this point, and if we want the acceleration, ma is equal to this force, or A is G times the mass of the Milky Way divided by RA squared. What you're gonna find is this force is huge, and this acceleration is tiny, okay? That's because the mass of the sun is like 10 to the 30th kilograms. This ends up being something like 10 to the 20th newtons. If I take away the mass of the sun, I get 10 to the minus 10 meters per second squared-ish. Basically, the acceleration due to the mass of the Milky Way is almost nothing at aphelion for the sun. You can see that in the solution. The total energy at any point for the sun is, again, the kinetic energy plus the potential energy, which you can find from GMM, Milky Way and Sun, over 2RA minus GMM over RA. Just compute that and you get it. You can also get the speed at perihelion from RA. VA is equal to RP VP. You can find RP from 2A minus RA. And we wanted VP, right? So VP is VA over RA over RP. So you can find that. That's not too hard to do. It's just plug and chug, really. There's an extra credit problem here that you can look at. Essentially, what this extra credit problem is about is that really, remember when we talked about being inside the Earth and what the gravity that affects you inside the Earth? Well, basically, the mass in this force, this GMM over R squared, this mass of the Milky Way is only the mass within the radius of the sun's orbit. Diana. So really, this is only the radius of the orbit of the sun, right? With respect to the center of the Milky Way. And that mass actually ends up only being about 1 part in 10,000 of the actual mass of the Milky Way. And so this is finding what the radius of a black hole would have to be with that same mass in order for you to be moving at the speed of light due to it. It's a weird problem. Look through the solution if it's interesting to you. If it's not interesting, just ignore it. But it's another one of those just plug and chug. It gives you the radius of the black hole, and it gives you the speed of light, and it asks you what this R should be if M is the mass of the Milky Way times 0.0001, right? And then lets you compare it to the sun's radius. That black hole will be about twice the sun's radius, I think. And that's pretty crazy, actually. That means that you would not be getting away from that object if you were within its radius, right? That's the radius where things can't escape. And if there were a black hole at the center of our solar system where the sun is, if you got within 2 radii of that black hole, radius of the sun, I should say, you would be swallowed and never return. Physics breaks down. Anyway, that's all well and good. So to recap really fast, and then we're done here. For fluids, P2 is equal to P1 minus rho G H2 minus H1, Pascal principle. What am I forgetting? Buoyancy, which is density of the liquid times the volume of the water displaced times G minus the density of the object times the volume of the object times G. And finally, static pressure, gravitational pressure, kinetic pressure is equal to static pressure 2 plus gravitational pressure 2 plus dynamic pressure 2, where H has to be in the opposite direction of gravity, and continuity equation. For gravity, since you can pause the video, I'm moving on. For gravity, F is equal to GMM over R squared. This is equal to MA, little m cancel. So A is GM over R squared. Kepler's first, second, and third law give RP plus RA is 2A. RP is A minus EA, RA is A plus EA. His second law gives that VA, RA is equal to VP, RP, or RA squared omega A is equal to RP squared omega P. And his last law is T squared is 4 pi squared G over whatever you're orbiting times A cubed. In our solar system, T squared is equal to A cubed if this is in Earth years and this is in meters. Otherwise, you need to use the full equation. And the last thing is that the energy, the kinetic energy, mv squared over 2 is equal to gmm over 2r. And the potential energy, which we usually call mgh, is gmm over r. And if you put those together, you get gmm over 2r minus gmm over r, which is minus gmm over 2r. But don't forget this part and don't forget this whole part, okay? Although I really doubt I'll give you a question on. Okay, so skip this stuff. But you better know how to do Kepler's laws, and you better know how to deal with the force of gravity. And you better know how to deal with the fluid stuff. And as we talked about earlier in the video, go through and make sure, just skip, Calvin, you can skip the potential energy and kinetic energy of gravity for the most part. If I do ask you about it, I will do something like this to remind you wherever the heck I did it. I know, right here. Here I told you the kinetic energy is that equation. Use that equation, find the mass. Just because this stuff is, honestly, you guys saw me earlier, and I didn't intentionally mess it up, but I don't care that you see me mess it up, because this stuff gets difficult and twisted and weird and dumb. I shouldn't say dumb. It's hard. It's a weird way to formulate things, and you have to formulate it that way because the potential energy of gravity has changed, as we talked about. That the 0 point is now infinitely far away. So this becomes your potential energy of gravity if you're at some r from the surface. Make sure you understand those homework problems, but as far as studying it for the test, don't sit there and rack your brain and fight with yourself and try to remember this and get all confused and spend 4 hours on one of these problems. I don't want you to do that. I want you to make sure that you know how to do Kepler's laws and use Kepler's laws to find like the period and the semi-major axis. Something that didn't show up in the exam but did show up on the quiz. Remember that E is equal to 0 as a circle, E equal to 1, or E less than 1 is a ellipse, E equal to 1 is a parabola, and greater is a hyperbola, right? So elliptical orbits or closed orbits only occur if E is less than 1. And for the planets, the closer that number is to 0, the more likely they formed with the sun in the disk. So all the planets have an E of less than like 0.2, and all comets and things like that are like 0.9. So just know what the ellipse eccentricity, the E, is telling you. It's telling you how squashed your ellipse is. Make sure you know that. And then on the fluids, as we talked about earlier, the real hard part is that you have to sometimes know what P1 or P2 is. So go back and watch that part of the video. But essentially, for Bernoulli's equation, you're finding P1, H1, V1, P2, H2, V2. For V1 and V2, they're related by A1, A2, the continuity equation. H1 and H2 are usually given to you, or that's what you're trying to find. And P1 or P2, you have to know that if the pipe's open, it's at atmosphere. This stuff we know from the buoyancy lab. This is pascals, and it only happens if you have an enclosed container with an input and an output. So this is really just almost like the continuity equation in a weird way. And this tells you the pressure if you change the height. So if you sink below the surface, or if you go above the surface of the Earth, the only thing I would caution you is make sure that H2 and H1 are correct sign-wise. Make sure that you know that H is positive away from the center of the Earth, right? So Y goes positive up in the air. Otherwise, you're going to get bad numbers. And your book kind of gets confusing about that. Just say that H2 is your final. So if you drop, H2 would be negative and H1 would be, I don't know, more positive. And if you went up, H2 would be greater than H1, I guess I should have said. As you go up in the air, the pressure goes down, right? And as you drop below the ocean, the pressure increases. So if this is a negative and it's greater than H1, then this whole term becomes positive. Just know how to read that equation and what that equation is telling you. But otherwise, it's really not that hard. If you're wondering what to study, just go through and study the homework problems and the final exam problems. If you have more time, go back through and maybe try to do some of the other problems in the book. But I tried to give you guys enough problems that you would have seen every weird thing that could come up. I hope. Okay. And then tomorrow, like I said, we're going to do like an hour-long lab. It's really fast. Basically, what I'm going to show you is I'm going to show you the iLab oscillating due to gravity and the spring. And it does a really nice, clean oscillation. You're going to get that data, and you're going to print or graph that data in Excel and get this nice waveform. That wave, we're going to translate, or we're going to model as a cos wave. And I'm going to show you how to find the amplitude, which is easy, omega, and the phase angle from that graph of that data. Don't forget, you got to turn your ILabs in this week. If you want to keep it till tomorrow, you can get your own data tomorrow, and I'll show you how to do that. It's really simple, but I'll provide the data for you in an Excel spreadsheet already. So you should be able to open up the Excel spreadsheet, highlight the data, graph it, and then what you're going to have to do is find the equation that you're going to use to model that motion. And then we're going to graph that superimposed on our first graph and see how well the model actually mimics the data. And it turns out really well. I should say this as a little preview. The goal for tomorrow is that we're going to have this IOLab hanging from a spring, right? Moving up and down. So MA is minus KX minus MG, right? This equation, we have no idea. If you try to solve this try to find X of T for this, good luck doing the differential equation, because that's M dx squared over dt squared plus K X of T is equal to negative mg, right? That is a really, well, it's not that hard, but it's a semi-hard equation. What we're going to assume is that it's modeled by some X of T is some amplitude, or X max times cos omega T minus phi. And we're going to look at a graph and figure out what this is and what this is and what this is, just looking at the graph. Write it down. We're going to put that equation in Excel with our same time data, and we're going to see that they're exactly the same. So it should be fun. It shouldn't take very long. You'll have a few questions and a little quick conclusion to write up. But honestly, I don't think it'll take, if you're really on it, it'll take you half an hour. If you're messing around, it might take you an hour, but it shouldn't take you very long to do tomorrow's lab, okay? And I'll be on Zoom with you for the full hour, hopefully, to get you guys done if you're having problems. And you can work in teams of 3. So 3 of you can work together and put your names on it if you want. I don't know how to do like breakout rooms. I'll figure that out for tomorrow. But yeah, I'll be there. You can ask questions. You can fill it out and turn it in tomorrow after you're done. And that'll be one of your lab grades, okay? So anyway, I'll see you guys tomorrow. I'm gonna get the force lab graded tonight, and people that I owe some stuff that I had to grade, I'm gonna get that done tonight, hopefully. Don't forget tomorrow night you have your buoyancy lab due, and don't forget your IO lab. Get your homework done. For those of you who weren't here, I think you were all here, but I need to say this again. Canvas doesn't calculate your grade correctly. Actually look at how much homework you've done, what percentage of the homework you've gotten credit for, and compare that to your homework grade and double check, because you might be looking at it, and because there's no zeros for homework you haven't turned in, it might say something like you have 100% for your homework when you've only done half your homework. If you've only done half your homework, you're going to lose 5%, and that might be enough to drop your grade. So word to the wise, get your homework in, please. Don't give up points for homework. You're just giving away your grade if you're not doing your homework. And while every teacher in the world says do your homework in physics, if you don't know already, you got to do homework, you guys. So I take it seriously. I want you to do your homework. And if your homework's not in, you're going to hurt your grade. Anyway, yeah, I'll talk to you guys tomorrow. Hopefully you're all staying healthy. No one's getting sick like I was. But I'll see you tomorrow. I'll post this soon. Bye, guys.